Thanks everyone for coming, and thanks Professor Nishimori for organizing this conference and letting me present my results. Also, I would like to thank my group at NASA, the Quantum Artificial Intelligence Lab, in particular Eleanor and Davide for their useful discussion, and also to thank Helmut for the many collaborations we have and the joint effort in the testing evaluation for the QEO. I would also like to thank IARPA within the QEO for the financial support. So today, I will present two things. My presentation will roughly divided in two parts. The first part will be related to the results on the exponential bias of a D-wave in first sampling of a degenerated ground state, while the second part will be related to the deceptive frustrated cluster model that yesterday Helmut has introduced. So what is the first sampling? So the first sampling is the ability of either a quantum or a classical algorithm to find homogeneously all the ground state of a degenerated problem. It is important because in some contexts, like machine learning, for example, finding a good variety of solutions is even more important than finding a single solution quickly. Also, from the benchmark point of view, it's way harder to find all the possible ground state of a degenerated problem rather than finding quickly the minimum energy. One of the first attempts to understand how a quantum annealer is good in first sampling was made by Professor Nishimori within Katsurabe and Matsuda in this paper of 2009. So in their paper, they have tried to study this toy model of 5 qubits, where the couplings are depicted here. And for this model, we have 3 degenerated ground states. Okay? What we have done is to numerically study the problem, because this problem can be exactly diagonalized. And what we have found is that in the end of the annealing, practically only 2 of the 3 states are sampled, both of them with a probability of 1/2, while 1 is exponentially depressed. So this was an early idea that a quantum annealer can be exponentially biased in finding a degenerated ground state. However, another point is that maybe non-stochastic driver Hamiltonian can mitigate this problem. I will not present the structure of a D-wave. Yesterday there were a lot of presentations about this, so I will go in directly to the results. So in order to understand if a D-wave is able to do first sampling, we have designed this kind of problems where couplings are randomly chosen among this Sidham set. And the idea to use this coupling is because we don't want a trivial degeneracy. We don't want that you can go from one ground state to another ground state just flipping a single qubit. We want that the ground state is sparse in the configurational landscape. And after a lot of work of big data, we were able to well control the degeneracy of this problem, which is given by this formula. What we have found is that, indeed, the D-wave is exponentially biased, as predicted. Here, in the x-axis, there are the indices of the ground state, while here we have the histogram of how many times the D-wave has found that solution. Note the logarithmic scale. So as you can see, there are some solutions which are exponentially depressed, while some of them are exponentially abundant. So this is in line with the original idea of Nishimori, Matsuda, and Katsurabe. However, one can say maybe this is not simply given by the D-wave. Maybe it is because of the instances. So we have tried to do the same for some of the best classical algorithms for the chimera architecture, which are the isoenergetic cluster method and HFS. And as you can see, this classical algorithm actually sampled fairly well. And also, it's not related how we do the histogram. If you look instance by instance, you can say that the D wave is not uniformly sampling, which means that the D wave is actually biased. So its point is an instance, and if you are front of the diagonal, it means that the D wave is not doing well in sampling for that instance. Another complaint could be maybe it's the noise. However, what we have done is to try two possible experiments. In one case, we have tried to rescale the problem Hamiltonian. So if you try, for example, to halve the energy of the problem Hamiltonian, the intrinsic noise is now twice as large as before, which means that effectively you are adding some noise to the problem. And as you can see, still we have an exponential bias. Also, we can try to add some extra noise. So we have tilted the coupling accordingly to this noise, and still we see this exponentially bias. So it's not the noise. And also, if we do this for classical algorithms, the classical algorithms are marginally affected by this noise. Finally, another possibility could be maybe it's because you're not really finding the ground state. So you are claiming that you have found all the ground state, but maybe it's not true. So we decided to do another further test. And the idea is this one. So instead of assuming that we know all the ground state of a problem, we just assume that the D wave has found all the possible solutions, so all the possible configuration given a specific energy. And we want just to understand if a D wave is biased within what the D wave has found. And we have done that for not only for the ground state, but for up to the 20th steady state. So practically, this is a measure to understand how it is biased, the D wave. Here we are in energy levels, and this is the baseline. So if you are far from this baseline, the D wave is biased. As you can see, for the ground state, the D wave is way biased, and you have to reach practically the 20th steady state just to have something which is not really biased. Which means that all this data suggests that the D wave is biased as a quantum annealer. And this is this is consistent with the theory that a quantum annealer should be biased when the ground state is degenerated. So for the first part, in conclusion, we have shown that the D wave is exponentially biased in sampling. However, we can try to mitigate this sampling problem. And one possibility is to explore different driver Hamiltonians. However, I believe that for non-toy problems, the complexity of this driver Hamiltonian, so the k-body interaction of the x, so for xxxx, should be very large. So you need a lot of x in order to have a good sampling. Another possibility is to add some knobs to tune. Right now, the D wave can, using the D wave is possible to adjust the delay in the annealing. So tuning those parameters, maybe we can mitigate the sampling problem. It is also important to understand why, from a theoretical point of view, there is a bias. And also, it is important to understand the implication from the many-body localization. Yesterday, Muhammad has explained that if you can reach this extended eigenstate, maybe you can somehow sampling better. So for the second part of my presentation, I will show some more results related to the deceptive frustrated cluster loop that Helmut has introduced yesterday. Just to resume what it is, a deceptive frustrated cluster loop, you start from a grid of L by L virtual variables, and then you construct, using these virtual variables, a frustrated cluster loop. as in King et al. Of 2015. But with the constraint that all the couplings must be plus or minus 1. Then you embed everything on the chimera so that all the intracouplings are ferromagnetic and fixed to 1, and then you scale all the intercell couplings by a factor lambda. The interesting thing of this model is that when lambda is close to 1, the ground state of this DFCL model is given by the solutions of the planar model, which is this virtual problem. And since we know how to find the ground state of a planar model for lambda close to 1, the problem is easy to solve. However, when lambda is larger than 1, at a certain point, these virtual variables just broke, in the sense that the ground state is not the solution for which all the virtual variables are aligned, but some of them are broken, so that there is no corresponding virtual problem that can help you to solve this problem in polynomial time. That's the reason why this problem becomes to be hard for lambda larger than 1. Here I'm showing the fraction of broken variables when lambda, by varying lambda. And as you can see, for lambda smaller than 3, practically you have few broken variables. But for lambda larger than 4, you have 1/10 of a variable to be broken. And since these virtual variables are randomly broken, you don't know how to find them. That's the hardness of this problem. Here I'm showing the results by fixing the size of the lattice by varying lambda. Just a small note. For HFS and D-Wave, I've used the usual way to run them. But for ICM, I consider the minimum between two possibilities. Either I start ICM with a random solution, or I start ICM from the ground state of a virtual problem. Why this? Because one can say, yes, you maybe have many broken variables, but these broken variables can be easily identified by just starting from a virtual problem and then simply try to optimize from them. In this way, I'm sure that it's not easy to start from a virtual solution to find the true ground state of a DFCL problem. Indeed, as you can see, HFS is practically independent of lambda, while the D-Wave is slightly dependent on lambda. And the reason is because when lambda is large, the noise starts to kick in. For ICM, you can see that for small lambda, the problem is quite easy, while for large lambda, it becomes to be hard. Here I'm showing some scatter plots where the size of the lattice is fixed, and I'm varying lambda. So practically, each point is an instance, and if the instance is in this side, the D-Wave Q, I forgot a 0 here. The 2000Q is better. So as you can see, for lambda equal to 1, HFS is always here, while ICM is always better, just because I use the trick to start from the ground state of a virtual problem. However, while I increase lambda, D-Wave is always better than HFS, even though some of the instances start to be hard also for the D-Wave. But if you look at ICM, you can see that there is a shift from the left to the right, so that all the instances start to be hard for ICM. In conclusion, we have devised a class of problem where the Wave 2000Q shows some advantages against ICM and HFS. And I want to remind you, using Helmut's words, that HFS is a tailored algorithm for the chimera architecture, which means that it is expected to be one of the fastest against D-Wave. And ICM is a non-tailored, multi-purpose, and actually very close to HFS in the performance. So I'm using two of the best algorithms. Also, our class cannot be trivially solved by a planar solvers, which means that we cannot use a backdoor to find the solution of these problems. Also, our approach can be used to devise a new class of problems to further exploit this kind of advantage which D-Wave has. Okay, thanks for your attention.
Questions?
Yeah, I would like to know why you think that you could eliminate bias. It seems to me almost unimaginable that any algorithm would produce solutions in the degenerate subspace with equal probability. And they do?
Okay.
But I mean, that sounds, and so and you know, you said you want to mitigate bias, but I certainly can't imagine a quantum algorithm would ever produce uniform distribution. And all classical algorithms produce uniform distributions? No. I mean, it sounds to me like producing a uniform distribution in the solution space, that sounds like as hard as counting or something in that space. Just sounds really hard. So I don't know why you want to do it.
Okay, let me say, not a uniform distribution because it's always impossible, as you said, but a fairly good distribution. I mean, not exponentially biased, as we found for the D-wave as alone, but as we found for the classical algorithm. And with respect to quantum algorithms, I would say that if you have an algorithm with many knobs that you can tune, maybe you can find the good parameters for your quantum algorithm so that for that specific class of problem, you can do a better job.
You say good is better, meaning in terms of reducing the bias.
Exactly.
Okay, I don't see that as good or better, but just different.
Yeah, indeed. Yeah.
If I just may briefly comment, Eddie, the issue is that you have states that are exponentially suppressed. And if you look at pedestrian algorithms like simulated annealing, that's not the case.
Okay.
No.
In the beginning of your talk, you presented a model with 5 spins that had 3 ground states. And quantum annealing was able to find 2. So if you run the system many times, will it be the same ground state that is not found? And if yes, is there a physical reason why?
Okay. The answer is no. Even if you try to run many times, you cannot find the ground state, and the physical explanation is one. Suppose you have these 3 ground states. For small transverse field, you have a splitting of the degeneracy because you have this avoid level crossing. So naturally, you have a splitting of this ground state, which means that one of the two has a higher energy very close to the end of a transverse field, when the transverse field is very small. So if you actually do quantum annealing, it means that you are reaching an eigenstate for small gamma, for small transverse field, so that it's not a superposition of all the 3, because there is this level splitting. No, it's not a spinal sinus effect. It's because there is the level splitting given by the lifting of the degeneracy due to the transverse field.
I'm afraid we're out of time. I could let you ask a question, but then he gets less time. So it's up to you to figure it out. But thank you so much.
You're welcome.